There is something strange about the universe that most of us never stop to consider. Not the distances, not the darkness, not the age of it all, though those things are remarkable enough on their own. The strange thing is something more fundamental than any of that. It is the possibility that space itself, the vast, silent emptiness that holds everything we have ever seen or measured or imagined, may not be what it appears to be. It may not, in any deep sense, be real at all. Tonight, we are going to sit with that idea. We are going to move through it slowly, because ideas like this become harder to hold on to the faster we move. Not rushing from room to room, but pausing in each doorway long enough to notice what the light is doing. At Sleepytime Universe, we explore the science of space slowly and without hurry, for curious minds that need a place to rest. This is not a story about illusions or tricks of perception. It is a story about what physicists and philosophers have begun to suspect after more than a century of careful, serious work, that the fabric of space, the container of all things, may be something that emerges from a deeper layer of reality that we have barely begun to see. Let's begin. Chapter 1. What space appears to be. As any honest exploration should, we begin with what we think we already know. Space, in the most immediate sense, is the emptiness between things. It is the gap between your hand and the wall across the room. It is the distance between the Earth and the Moon, between the Sun and the nearest neighboring star, between one galaxy and the next. It is the medium through which light travels, and the arena in which gravity reaches across unimaginable distances to draw things together. Space is, in the most ordinary understanding of the word, the place where everything happens. For most of human history, that was enough of a definition. People did not need to ask what space was made of, or whether it had a fundamental nature of its own. It was simply there, silent, vast, and self-evident. The sky above was space. The darkness between the stars was space. You did not question it any more than you questioned the ground beneath your feet. But the moment natural philosophers began trying to describe the universe mathematically, space became something that needed to be defined with more precision. And the more precisely they tried to define it, the stranger it became. The ancient Greeks imagined a cosmos arranged in nested spheres, each one carrying a celestial body as it rotated around the Earth. The space between those spheres was not thought to be truly empty. It was believed to be filled with a perfect, invisible substance they called the ether, a material that gave the heavens their structure and allowed the stars to move in their great circles overhead. Truly empty space, a pure and absolute vacuum, was considered philosophically impossible. Nature, the Greeks believed, would not permit a void. This picture held, in various forms, for nearly 2,000 years. Astronomers refined it, mathematicians extended it, and generation after generation inherited it. The details changed as observations grew more precise, but the basic intuition persisted. Space was a setting, a stage, and something had to fill it. It was Isaac Newton, working in the latter half of the 17th century, who gave the Western understanding of space its most powerful and enduring scientific form. In Newton's picture of the universe, space was absolute. It existed independently of everything within it, a fixed, infinite, three-dimensional expanse against which all motion could be measured. Time was similarly absolute, flowing at the same rate everywhere, untouched by what was happening around it. Together, absolute space and absolute time formed the scaffolding of reality. They were not influenced by matter or energy. They were not created by the presence of objects. They simply existed as a kind of eternal background, and everything else moved within them. This framework was extraordinarily successful. It allowed scientists to calculate the orbits of planets with remarkable accuracy, to predict the paths of comets, to describe the motion of falling objects and the behavior of ocean tides. For more than 2 centuries, Newtonian mechanics stood as perhaps the greatest achievement in the history of science. Space, in Newton's formulation, seemed to have been understood once and for all. But there was a philosopher who was not satisfied, and his dissatisfaction, expressed quietly in the early 18th century, would turn out to be far ahead of its time. Gottfried Wilhelm Leibniz, a contemporary and rival of Newton, argued that the concept of absolute space was a philosophical mistake. Space, Leibniz insisted, was not a container that existed independently of its contents. It was simply a way of describing the relationships between objects. There was no space apart from the things in it. If you removed every object from the universe, you would not be left with an empty space. You would be left with nothing at all, because space was never a thing in itself. It was a description of how things related to one another, and nothing more. Leibniz called this the relational view of space. It was a subtle but profound distinction. In Newton's world, space was real and independent. It would exist even if the universe were completely empty. In Leibniz's world, space was a kind of abstraction, a useful language for describing positions and distances, but not something that had an existence of its own. This disagreement was never resolved in their lifetimes. Newton's framework worked so well, so precisely, and so consistently across so many different phenomena, that Leibniz's objection remained a philosophical curiosity rather than a scientific challenge. The universe behaved as though space were absolute, and for practical purposes, that seemed to settle the matter. It took another 2 centuries for the question to return with any urgency, and when it did, it arrived not through philosophy, but through physics, through a series of experiments and theoretical discoveries that began to pull at the edges of Newton's picture in ways that could not be ignored. The first thread to come loose was light. By the middle of the 19th century, physicists had established that light was a wave. Waves, in every other context, required a medium to travel through. Sound waves moved through air. Ocean waves moved through water. It seemed natural to assume that light waves moved through something as well, and that something was given the old Greek name, the ether. Scientists believed that space was filled with this invisible substance, and that light propagated through it the way sound propagates through a room. In 1887, 2 American physicists named Albert Michelson and Edward Morley designed an experiment to detect the ether directly. Their reasoning was straightforward. If the Earth was moving through a stationary ether as it orbited the Sun, then light traveling in the direction of that motion should behave slightly differently from light traveling against it, in the same way that a swimmer moves at different speeds, depending on whether they are swimming with or against a current. The difference would be small, but Michelson and Morley had built an instrument sensitive enough to measure it. They found nothing, no difference at all. Light moved at the same speed regardless of direction. The ether, which had been assumed to fill all of space and give it substance, showed no sign of existing whatsoever. The result was deeply unsettling. If there was no ether, what was space? What was light moving through? And if the speed of light was always the same regardless of how the observer was moving, what did that mean for Newton's absolute fixed backdrop against which all velocities were supposed to be measured? These questions sat at the center of physics for nearly 2 decades, unresolved and uncomfortable. And then, in 1905, a young patent clerk in Bern, Switzerland, who had been thinking very carefully about what it actually means to measure distance and time, published a paper that changed everything. Chapter 2: Einstein and the Flexible Stage. Albert Einstein did not begin with mathematics. He began with imagination. Before he wrote a single equation in what would become his special theory of relativity, Einstein had spent years asking himself a deceptively simple question. What would it look like to ride alongside a beam of light? If you could somehow travel at the same speed as light, would the light wave appear to stand still beside you, frozen in space, the way a running man appears motionless to someone running at exactly the same pace? And if so, what would that mean for the nature of light and for the nature of space and time? The more carefully he sat with this question, the more he became convinced that Newton's picture of absolute space and absolute time contained a hidden assumption that the universe did not actually support. Newton had assumed that measurements of distance and duration were the same for all observers, regardless of how fast they were moving. Two people measuring the length of the same object, or the time between the same two events, would always get the same answer. That was Newton's world. Einstein proposed something different. He proposed that the speed of light was the constant, not the measurements of space and time. Light always travels at the same speed for every observer, no matter how that observer is moving. And in order for that to be true, space and time themselves had to be flexible. They had to stretch and compress depending on the motion of the observer. This was not an easy idea to absorb. It meant that two observers moving at different speeds would genuinely measure different distances between the same 2 points and different durations between the same 2 events. Neither would be wrong. Both measurements would be correct, within their own frame of reference. There was no privileged absolute frame against which all others could be judged. Newton's fixed grid, the eternal backdrop of absolute space and time, did not exist. Special relativity, as this theory came to be called, dissolved the boundary between space and time in a way that had never been anticipated. Instead of two separate things, a three-dimensional space and an independent one-dimensional time, Einstein described a single four-dimensional structure that physicists came to call spacetime. Space and time were not separate stages. They were two aspects of one unified fabric, and they were woven together in such a way that what one observer experienced as purely a distance in space, another observer moving at a different speed would experience as a mixture of distance and time. The implications of this were strange and far-reaching. A clock on a fast-moving spacecraft would tick more slowly than a clock left behind on Earth. A ruler moving at high speed would appear shorter along the direction of motion than the same ruler at rest. These were not optical illusions or measurement errors. They were genuine features of the structure of spacetime, confirmed by experiment after experiment throughout the 20th century and beyond. But special relativity, remarkable as it was, still treated spacetime as a fixed background. It had replaced Newton's absolute space and absolute time with a unified spacetime fabric. But that fabric was still flat, still static, still a stage on which events played out without being affected by what was happening within it. Matter moved through spacetime. Spacetime itself did not move. That changed 10 years later, when Einstein completed his general theory of relativity in 1915. General relativity was a deeper and more radical proposal. It described gravity not as a force transmitted across space, the way Newton had imagined it, but as a curvature in the fabric of spacetime itself. Mass and energy did not just sit inside spacetime. They shaped it. They bent it, warped it, stretched it, and other objects moving through that warped space-time followed the curves, which is what we perceive as gravitational attraction. The image that physicists often use is a heavy ball placed on a stretched rubber sheet. The ball creates a depression in the sheet, and smaller balls rolled nearby curve toward it, following the contour of the surface rather than being pulled by any direct force. The analogy is imperfect, but it captures something essential. In general relativity, gravity is geometry. The shape of space-time determines how matter moves, and matter determines the shape of space-time. This was an extraordinary shift. Space was no longer a passive container. It was an active participant in the physics of the universe. It could curve and bend. It could expand or contract. It could, under the right conditions, ripple like the surface of a pond disturbed by a stone. And those ripples, which we now call gravitational waves, were detected directly for the first time in 2016, a full century after Einstein predicted them. The universe, it turned out, was not sitting inside space. Space was something that the universe was made of, something dynamic, responsive, and deeply physical. When two black holes collide a billion light-years away, the event does not merely send a signal through space. It sends a shudder through the fabric of space itself, and that shudder eventually reaches us, stretching and compressing the very distances between objects as it passes. General relativity was confirmed by observation almost immediately. In 1919, the British astronomer Arthur Eddington led an expedition to observe a solar eclipse and measured the bending of starlight around the sun, exactly as Einstein's equations predicted. The result made headlines around the world. Newton's picture of space had been replaced, and what replaced it was stranger and more wonderful than anyone had imagined. And yet, even within this new picture, space was still treated as a real and fundamental thing. It curved, it rippled, it expanded, but it was still the basic substance of the universe, the medium in which everything existed. Einstein had transformed the nature of space, but he had not questioned whether space was real. That question would come later, from a direction no one expected, because while Einstein was rewriting gravity, a completely separate revolution was taking place in physics, one that would raise even deeper questions about the nature of reality and about whether space, at the smallest scales of existence, has any meaning at all. Chapter 3. The Quantum Puzzle. When physicists turned their attention to the very small, they found a world that obeyed entirely different rules. In the early decades of the 20th century, a new theory began to take shape, built piece by piece from experiments that kept returning results that classical physics could not explain. Atoms did not behave like miniature solar systems. Light did not behave purely like a wave, nor purely like a particle, but like something that had no clean everyday equivalent at all. Energy did not flow continuously, but arrived in discrete packets, as though the universe had a smallest possible unit of exchange that could not be divided any further. This new framework came to be called quantum mechanics, and it described the behavior of matter and energy at the smallest scales with extraordinary precision. It remains to this day the most accurately tested theory in the history of science. Its predictions have been confirmed to a degree of precision that has no parallel in any other field of human knowledge. But quantum mechanics came with a cost. The cost was clarity. The theory worked. It produced correct answers with breathtaking reliability. But what it was actually saying about the nature of reality was deeply, stubbornly unclear. In classical physics, an object had a definite position and a definite velocity at every moment in time. You could, in principle, know exactly where something was and exactly how fast it was moving. The universe was, in this sense, a machine whose future states could be calculated precisely from its present state, if only you had enough information and enough computing power. Quantum mechanics dismantled this picture entirely. At the quantum scale, a particle does not have a definite position until it is measured. Before measurement, it exists in a superposition, a combination of all the possible positions it could occupy, each weighted by a probability. When a measurement is made, the superposition collapses, and the particle is found in one specific location. But before that measurement, the question of where the particle is does not have a definite answer. It is not that we do not know where it is. It is that the concept of a precise location does not apply. This was deeply troubling to many physicists, including Einstein, who famously refused to accept that the universe could be fundamentally probabilistic. He spent decades searching for a deeper layer of reality beneath quantum mechanics, a set of hidden variables that would restore the determinism and clarity of classical physics. He never found it, and the experiments that were conducted in the decades after his death strongly suggested that no such hidden layer exists. The universe, at its smaller scales, appears to be genuinely and irreducibly probabilistic, but the strangeness does not stop there. Quantum mechanics also revealed a phenomenon called entanglement, which Einstein himself described as spooky action at a distance, and which turns out to be one of the most important clues in the entire puzzle of whether space is real. When two quantum particles interact in the right way, they can become entangled. From that point on, the properties of the two particles are correlated in a way that cannot be explained by any information they carry with them. If you measure one particle and find that its spin is pointing upward, you instantly know that its entangled partner, no matter how far away it might be, will be found with its spin pointing downward. The correlation is perfect, and it holds regardless of the distance between the particles. This would not be remarkable if the particles were simply carrying matching instructions from the moment of their interaction. The way a pair of gloves separated into two boxes will always reveal one left and one right when opened, regardless of distance. But the experimental evidence, confirmed decisively through a series of tests beginning in the 1980s and refined continuously since, rules out this explanation. The particles are not carrying hidden matching instructions. The correlation is established at the moment of measurement, not before. What this means for space is profound and deeply unsettling. In our ordinary experience, things that are far apart are genuinely separate. The distance between them is real. What happens here does not instantly affect what happens there. This intuition, that spatially separated things are independent, is so fundamental to our picture of reality that physicists give it a name: locality. And quantum entanglement appears to violate it, not in a way that allows information to travel faster than light. The correlations cannot be used to send a signal, but in a way that suggests the two particles are, in some sense, that defies easy description, not truly separated at all. The distance between them, which appears so real and so definitive from the outside, does not seem to be the deepest truth about their relationship. This was the crack in the foundation that later theorists would begin to widen. If two entangled particles on opposite sides of the universe share a connection that space cannot sever, then perhaps space is not the fundamental structure we take it to be. Perhaps distance, the very thing that space is supposed to provide, is not a basic feature of reality, but something that emerges from a deeper layer of connections that has nothing to do with geometry at all. The physicist John Bell formalized this intuition in 1964, when he derived a mathematical test, now known as Bell's theorem, that could determine whether the correlations in quantum experiments could be explained by any local hidden variable theory, or whether they required something more radical. Experiments testing Bell's theorem, most famously conducted by Alain Aspect and his colleagues in 1982, and refined by many others in the decades since, have consistently confirmed that local hidden variables cannot explain what is observed. The universe is, in the technical language of physics, non-local. Something is connecting things across space in a way that space itself cannot account for. And if space cannot account for its own contents, if the connections between particles run deeper than the distances between them, then the question of whether space is truly fundamental becomes not a philosophical curiosity, but a live and urgent problem at the heart of physics. The two great theories of the 20th century, general relativity, which describes the large-scale structure of the universe, and quantum mechanics, which describes its smallest constituents, each pulled at the concept of space from a different direction. General relativity made space dynamic and physical, something that could bend and ripple. Quantum mechanics suggested that the deepest relationships in nature did not respect the distances that space was supposed to enforce. And the two theories, despite their individual successes, refused to fit together. Every attempt to combine them, to write a quantum theory of gravity, to describe space-time itself in quantum terms, ran into mathematical difficulties so severe that they suggested something was fundamentally wrong with the picture, not with one theory or the other, but with the assumption they shared, that space, in some form, was the basic arena in which physics happened. That assumption, held almost universally since the first humans looked up at the sky, was about to be seriously questioned. Chapter 4. When Gravity Met the Quantum. The conflict between general relativity and quantum mechanics is one of the most important unsolved problems in all of science. It is not a disagreement about minor details or edge cases. It is a fundamental incompatibility between the two most successful theories ever constructed. A contradiction so deep that most physicists believe it cannot be resolved without changing our understanding of something very basic about the nature of reality. General relativity describes a smooth, continuous space-time. In Einstein's picture, the fabric of the universe is like a vast, seamless sheet that can be curved and stretched, but never torn or broken. There are no gaps, no graininess, no smallest unit of space. The geometry is continuous all the way down, no matter how far you zoom in. Quantum mechanics, by contrast, is a theory of discreteness. It describes a world that comes in packets. Quanta of energy, quanta of action, specific allowed states with nothing permitted in between. When quantum mechanics is applied to fields, it produces particles. When it is applied to the electromagnetic field, it produces photons. The natural expectation is that when it is applied to the gravitational field, to space-time itself, it should produce a quantum of gravity, a particle that physicists call the graviton. But every attempt to apply the standard tools of quantum mechanics to general relativity produces nonsense. The calculations generate infinities, not the manageable kind that appear in other quantum theories, and can be carefully handled through a process called renormalization, but a cascade of infinities that cannot be tamed by any known mathematical technique. The theory breaks down, and it breaks down in a way that signals something more than a technical problem. It signals a conceptual mismatch. The place where this mismatch is most dramatic is the singularity, the point at the center of a black hole, or the moment of the Big Bang, where general relativity predicts that the density of matter and the curvature of space-time become infinite. These infinities are not physical. They are the theory's way of announcing that it has been pushed beyond its domain of validity. At these extreme scales, where the curvature of spacetime becomes comparable to the smallest quantum scales of length and time, neither general relativity nor quantum mechanics can be trusted. A new theory is needed, one that can describe gravity in quantum terms. That new theory does not yet exist in its final form, but several serious attempts have been made, and what they share is remarkable. Almost without exception, the candidate theories of quantum gravity suggest that space-time, the smooth, continuous fabric that Einstein described, is not fundamental. It is something that emerges from a deeper level of reality that doesn't itself involve space or time at all. One of the most developed of these approaches is string theory. In its original form, string theory proposed that the fundamental constituents of nature are not point particles, but tiny, one-dimensional vibrating strings of energy. Different vibrational modes of these strings correspond to different particles, including the graviton. The theory requires additional spatial dimensions beyond the 3 we experience. As many as 6 or 7 extra dimensions, curled up so tightly at every point in space that they are far too small to detect with any current instrument. String theory has produced a remarkable result that is directly relevant to the question of whether space is real. In the late 1990s, the physicist Juan Maldacena discovered a precise mathematical equivalence between a theory of gravity in a region of space and a quantum theory with no gravity defined only on the boundary of that region. This equivalence is known as the ADS/CFT correspondence, and it has been one of the most studied and debated results in theoretical physics ever since. What Maldacena's correspondence suggests is startling. The physics happening inside a volume of space, including all the gravitational dynamics, all the curvature of space-time, all the behavior of matter within that volume, can be completely described by a theory that lives on the surface enclosing that volume, in one fewer dimension, with no gravity at all. Every event inside the volume corresponds precisely to something happening on the boundary. Nothing is lost. The two descriptions are mathematically identical. This is known as the holographic principle, and it carries a deeply unsettling implication. If the complete physics of a 3-dimensional volume can be encoded on a 2-dimensional surface, then in what sense is the 3rd dimension real? The interior of the volume, with all its apparent depth and extension, may be a kind of projection, something that emerges from the boundary description, the way a hologram produces the appearance of 3-dimensional structure from a 2-dimensional film. The holographic principle did not begin with Maldacena. Its roots go back to the work of Stephen Hawking and Jacob Bekenstein in the 1970s, who discovered something deeply puzzling about black holes. The entropy of a black hole, a measure of the information it contains, is proportional not to its volume, as you might expect, but to the area of its event horizon, the surface that surrounds it. This was the first hint that the information content of a region of space is determined by its boundary, not its interior. Maldacena's result gave that hint a precise mathematical form. The holographic principle suggests that one of the 3 dimensions of space we experience may not be fundamental. It may be emergent, a feature that appears in our description of reality but does not correspond to anything basic in the underlying structure of things. And if one dimension can be emergent in this way, the natural question is whether all dimensions of space might be emergent, whether space itself, in its entirety, is something that arises from a deeper description that contains no space at all. A second approach to quantum gravity, called loop quantum gravity, reaches a similar destination by a different route, Loop quantum gravity attempts to quantize spacetime directly, applying the mathematical tools of quantum mechanics to the geometry of space itself. What it finds is that space, at the smallest scales, is not continuous. It is granular. It comes in discrete chunks, tiny units of volume and area below which the concept of distance loses meaning. The smooth space-time of general relativity is, in this picture, an approximation, something that looks continuous from a distance, the way a sandy beach looks smooth from an aeroplane, but which reveals its grainy structure when examined up close. In loop quantum gravity, the smallest meaningful unit of length is the Planck length, approximately 1.6 times 10 to the power of negative 35 meters. This is incomprehensibly small. A proton is roughly 10 to the power of negative 15 meters across, which means the Planck length is 20 orders of magnitude smaller than a proton. No instrument built by human hands could probe distances anywhere near this scale. But theoretically, below this length, the concept of space as a geometric continuum breaks down entirely. Both of these approaches, the holographic picture from string theory and the granular picture from loop quantum gravity, point in the same direction. Space, at its deepest level, is not what it appears to be. It is not the smooth, continuous three-dimensional expanse that Newton imagined, nor even the dynamic curved fabric that Einstein described. It is something that emerges, something that appears to exist at the scales we can observe, but which dissolves into something else entirely when examined at the most fundamental level. The stage, it seems, is not made of stage material. It is made of something else, something that does not look like space at all. And the appearance of space is a large-scale pattern that emerges from it, the way temperature emerges from the motion of molecules, or the way the smoothness of water emerges from the chaotic interactions of individual atoms. Real at the scale where we encounter it, but not fundamental, not the bottom of things. Chapter 5. The idea of emergent space. There is a word that keeps appearing in the most serious discussions about the nature of space, and it is worth pausing to understand what it means. The word is emergent. It is a word that physicists and philosophers use to describe properties or structures that are real and measurable at one level of description, but which do not exist as fundamental features at a deeper level. They arise, they appear, they emerge from something else. Emergence is not an exotic or unfamiliar idea. It is all around us, woven into the most ordinary features of the world. Temperature is a good example. When you hold your hand near a warm surface and feel the heat, that sensation corresponds to something real, a measurable quantity that thermometers can detect and that affects the behavior of everything around it. But temperature does not exist at the level of individual molecules. A single molecule does not have a temperature. Temperature is what happens when you have a very large number of molecules moving and colliding, and it describes the average energy of that motion in a way that becomes meaningful only at the collective scale. It emerges from the microscopic behavior without being present in it. Wetness is another example. A single water molecule is not wet. Wetness is a property that arises when enormously many water molecules are together and interacting in a particular way. The individual constituents do not possess the property. The property belongs to the collective, and it is entirely real. You can feel it, measure it, build technologies around it, even though it has no counterpart at the level of the fundamental ingredients. Consciousness may be the most profound example of all, though it remains the least understood. The individual neurons in a human brain do not think or feel. They fire electrochemical signals, they form connections, they respond to inputs. but from the coordinated activity of roughly 86 billion of them, something arises that can contemplate its own existence, feel wonder at the night sky, and ask questions about the nature of reality. How that happens, how subjective experience emerges from physical processes, remains one of the deepest unsolved problems in science. But almost no serious thinker doubts that it does happen, that mind is in some sense emergent from matter. The proposal now being seriously explored in theoretical physics is that space belongs in this category, that the three dimensions we move through, the distances we measure, the geometry that holds the planets in their orbits and the galaxies in their great clusters, all of this is emergent. It arises from something deeper that doesn't itself have spatial properties. The distances are not fundamental. The geometry is not fundamental. What we call space is a large-scale approximation, like temperature, like wetness, like the smoothness of a liquid. Real enough at the scale where we encounter it, but dissolving into something unrecognizable when you look closely enough. This is a difficult idea to hold in the mind, because space feels so immediate and so unavoidable. You cannot step outside of it. You cannot find a vantage point from which to observe it as a phenomenon, the way you can observe temperature with a thermometer or wetness with your fingertip. Space is the medium of all observation, which makes it very hard to question. But the theoretical arguments for emergent space have grown steadily more compelling, and they now come from several independent directions that converge on the same conclusion. One of the most striking comes from the study of entanglement, the same quantum phenomenon we encountered in an earlier chapter, where particles separated by vast distances share correlations that cannot be explained by any local mechanism. In recent years, physicists have begun to suspect that entanglement is not merely a strange feature of quantum mechanics. It may be the mechanism by which space itself is built. The idea, developed most prominently by physicists Mark van Ramsdonk and others working at the intersection of quantum information theory and gravity, is that the geometry of spacetime is directly related to the pattern of quantum entanglement in the underlying quantum state of a system. Regions of space that are close together correspond to strongly entangled quantum degrees of freedom. Regions that are far apart correspond to weakly entangled ones. Distance in this picture is not a primitive feature of reality. It is a measure of entanglement. Space is woven from quantum connections. Van Ramsdonk explored this idea through a striking thought experiment. Imagine taking a system described by the holographic principle, a quantum system on a boundary that corresponds to a region of space with gravity in its interior. Now imagine gradually reducing the entanglement between different parts of the boundary system. What happens to the interior geometry? According to the mathematics, the interior space begins to pull apart. Regions that were connected become disconnected. The geometry fragments. If you reduce the entanglement to zero, the interior space tears in two. Two completely separate regions with no connection between them. The implication is remarkable. Space, in this picture, does not come first and then get filled with entangled quantum systems. The entanglement comes first, and space is what it looks like from the outside. The connectivity of space, the fact that here and there are joined by a continuous geometry, is a reflection of the quantum entanglement between the underlying constituents of reality. Sever the entanglement, and you sever the space. This resonates deeply with what the experiments on Bell's theorem have been telling us for decades. When two entangled particles share a correlation that transcends the distance between them, perhaps they are not really separated at all. Not at the level of the deeper reality from which space emerges. The distance between them is a feature of the emergent geometry, not of the fundamental structure. At the level where the real physics is happening, they may be as close as two thoughts in the same mind. Another line of evidence comes from the behavior of black holes and the deep puzzle of information. When matter falls into a black hole, general relativity says that the information describing that matter, every detail of its quantum state, is lost behind the event horizon forever. But quantum mechanics insists that information cannot be destroyed. It may be scrambled, hidden, redistributed, but it cannot vanish. The two theories are in direct conflict. The resolution that most physicists now favor is that the information is somehow encoded on the surface of the black hole and eventually released in an extraordinarily scrambled form in the radiation that Hawking showed the black hole must emit. The interior of the black hole, all that volume of space inside the event horizon, does not contain information that is independent of the boundary. The surface is the fundamental description. The interior is, in some deep sense, a derived one. This line of thinking has led to what is sometimes called the black hole information paradox, being resolved not by changing quantum mechanics, but by reconsidering the nature of the interior space. If the interior is emergent, if it arises from the surface description rather than existing independently, then the apparent paradox dissolves. There is no truly independent interior in which information can be permanently lost. The interior is a projection, and projections do not swallow things that the original cannot account for. What emerges from all of this is a picture that would have seemed like science fiction a generation ago, but is now the subject of serious work at the world's leading research institutions. Space is not the container of reality. It is a pattern in reality, a large-scale structure that emerges from something deeper, something that does not look like space, something built from relationships and entanglements and information, rather than from geometry and distance and dimension. We do not yet know what that deeper something is. We do not have its complete mathematical description. The theory of quantum gravity that would make all of this precise and testable is still being built, piece by careful piece, by physicists working at the edges of what is currently understood. But the direction is clear, and it points away from space as a fundamental thing, and towards space as something that the universe produces, something real at our scale, but not real all the way down. Chapter 6. What reality might be made of? If space is not fundamental, if it emerges from something deeper, then the obvious and uncomfortable question is, what is that something deeper made of? This is the point where physics and philosophy begin to overlap in ways that are difficult to separate cleanly. The honest answer is that we do not know. The deeper layer of reality, if it exists, has not been directly observed. It cannot be, at least not with any instrument currently available to us, because it operates at scales so far below anything we can probe that the distance between our best experiments and that level of reality is greater than the distance between a single atom and the observable universe. We are reasoning toward it from the top down, from the behavior of things we can observe, inferring the nature of a foundation we cannot yet see. But reasoning from the top down is not nothing. It is, in fact, how most of the deepest discoveries in physics have been made. The existence of atoms was inferred from the behavior of gases long before anyone could observe an atom directly. The existence of black holes was a mathematical consequence of general relativity decades before any observational evidence confirmed them. The existence of gravitational waves was predicted in 1915 and not detected until 2016. Physics has a long history of the invisible being real and of the real being invisible until the instruments catch up with the theory. So what do the theories suggest? What might the fundamental substrate of reality, the thing that space emerges from, actually be? The most mathematically developed answer, at least within the framework of the holographic principle, is that the fundamental ingredients are quantum degrees of freedom. This is a somewhat abstract phrase, and it is worth unpacking carefully. A degree of freedom in physics is simply something that can be in different states. A coin is a system with 2 degrees of freedom, heads or tails. A quantum degree of freedom is the same idea applied to the quantum world, where a system can be in a superposition of states and where its properties are defined not by classical values, but by quantum amplitudes and probabilities. In the holographic picture, the fundamental description of a region of spacetime is a quantum system living on its boundary, a collection of quantum degrees of freedom whose interactions and entanglement patterns give rise to the geometry of the interior. These boundary degrees of freedom are not particles moving through space. They are not fields defined at points in a spatial grid. They are abstract quantum objects whose relationships to one another are described purely in terms of information. What states they can occupy, how they are entangled, how their quantum states evolve over time. Space, in this picture, is what the pattern of their entanglement looks like when viewed from a certain perspective. It is a geometric translation of a fundamentally non-geometric reality. The distances and dimensions that we experience are a kind of readout, a way of describing the information structure of the boundary system in terms that make intuitive sense at the scales we inhabit. Some physicists have pushed this idea even further, suggesting that the most fundamental description of reality might be purely informational. Not matter, not energy, not fields, not even quantum degrees of freedom in the usual sense, but information itself in the most abstract mathematical sense of the word. The physicist John Archibald Wheeler, one of the great figures of 20th century physics, coined a phrase that has become something of a motto for this view: it from bit. His proposal was that every physical thing, every particle, every field, every dimension of space derives its existence from information, from answers to yes or no questions, from binary choices at the most fundamental level. Wheeler arrived at this idea late in his career, after decades of working at the center of both general relativity and quantum mechanics. He had helped develop the concept of the black hole, had worked closely with both Einstein and Bohr, and had spent a lifetime thinking about what the 2 great theories of the 20th century were trying to tell us about the nature of reality. His conclusion was that the universe, at its deepest level, is not made of stuff. It is made of distinctions. It is made of information about itself. This idea has been developed and extended by many physicists since, most notably in the work on quantum information theory and its connections to gravity. The phrase has been updated by some to it from qubit, replacing the classical binary bit with the quantum bit, the qubit, which can exist in superpositions of 0 and 1 simultaneously. In this view, the universe is a quantum information processing system, and what we call physical reality, space, time, matter, energy, are all emergent properties of the computation. This is not, it should be said, a claim that the universe is a simulation running on some external computer. That interpretation, while popular in certain circles, goes beyond what the physics actually requires. The claim is more subtle and more interesting than that. It is that the mathematical structure of reality, at its most fundamental level, resembles the mathematical structure of information processing, and that this resemblance is not a coincidence or an analogy, but a deep truth about what existence is made of. Another possibility, less developed but philosophically rich, is that the fundamental substrate is relational in the sense that Leibniz originally proposed, that reality, at its deepest level, consists not of things, but of relationships between things, not objects with properties, but pure relations from which objects and properties emerge as derived concepts. This view, sometimes called relational quantum mechanics, and developed in detail by the physicist Carlo Rovelli, proposes that the properties of a quantum system do not exist absolutely, but only relative to other systems. There is no view from nowhere, no God's eye perspective from which the state of the universe can be described independently of all observers. Every description is a description from somewhere, relative to something. In Rovelli's picture, space is one of the things that emerges from these fundamental relations. It is not the container of the relations. It is produced by them. The geometry of the world is a feature of how things relate to one another, not a pre-existing stage on which the relating happens. This is Leibniz's intuition, refined and extended by 3 centuries of physics, returned to relevance by the failures of every attempt to quantize spacetime directly. What all of these proposals share is a movement away from space as the given and toward space as the derived. Whether the fundamental layer is quantum information, relational degrees of freedom, abstract mathematical structure, or something not yet named, the consensus is growing that it does not look like space. It does not have dimensions in the way we experience dimensions. It does not have distances in the way we experience distances. It is something prior to geometry, something from which geometry crystallizes under the right conditions, the way ice crystallizes from water when the temperature drops below a certain threshold. Ice is real. You can hold it, weigh it, build with it, but it is not fundamental. It is water in a particular configuration, water that has organized itself into a rigid lattice under the influence of temperature and pressure. The lattice is real. The geometry of the crystal is real. But the geometry is not the bottom of things. The bottom of things is the water. And the water, in turn, is molecules. And the molecules are atoms. And the atoms are quantum fields. And the quantum fields are what? That is the question that sits at the heart of modern physics, unanswered and urgent. Space may be the ice in this analogy, real enough at our scale, solid enough to build a universe on, but not the final word on what reality is made of. Chapter 7. The Experience of Space. There is a question that the physics alone cannot fully answer, and it is in some ways the most immediate question of all. If space is emergent, if it is not fundamental, if it arises from something deeper that has no geometry, then why does it feel so real? Why does the distance between here and there seem so absolute, so undeniable, so impossible to doubt? This is not a naive question. It is one that any serious account of emergent space has to address, because the feeling of space is not a peripheral feature of human experience. It is central to it. Every perception you have ever had is spatial. Every object you have ever seen occupies a location. Every movement you have ever made is a traversal of distance. The sense of being somewhere, of having a position in a world that extends in all directions around you, is so fundamental to conscious experience that it is difficult even to imagine what experience without it would be like. The answer begins with the observation that emergence does not mean illusion. Temperature is emergent, but it is not a trick your mind plays on you. It is a real and measurable feature of the world at the scale where you encounter it. The fact that it dissolves into molecular motion at a deeper level does not make it less real at the level of your thermometer or your skin. Emergent properties are genuine properties. They simply are not the deepest properties. Space, in the same way, would be genuinely real at the scale of human experience, even if it emerges from something non-spatial at a deeper level. The distances you measure with a ruler are real distances. The geometry that keeps the planets in their orbits is real geometry. The curvature that Einstein described is real curvature. None of that is called into question by the possibility that space is emergent. What is called into question is only whether space is the final layer, whether the description in terms of geometry and distance is the most fundamental description available. But there is a deeper point here, one that touches on the relationship between perception and reality in a way that has occupied philosophers for a very long time. Our experience of space is not a direct readout of the structure of the external world. It is a construction, something that the brain builds from sensory information according to its own internal rules and categories. The philosopher Immanuel Kant, writing in the 18th century, argued that space was not a feature of the external world at all. It was, he proposed, a form of intuition, a structure that the human mind imposes on experience in order to make sense of it. We do not perceive space because space is out there. We perceive space because our minds are organized in such a way that all experience is automatically arranged in spatial terms. Space, for Kant, was the lens through which the mind sees the world, not a feature of the world itself. Kant's argument was philosophical rather than scientific, and it cannot be directly tested. But it raises a question that modern neuroscience has begun to explore in earnest. How does the brain construct the experience of space? And what does that construction tell us about the relationship between our perception of the world and the world as it actually is? What neuroscience has found is that the brain's representation of space is active, not passive. The sense of being located in a three-dimensional environment does not arrive pre-assembled from the senses. It is built continuously and dynamically from a combination of visual information, auditory cues, proprioceptive signals from muscles and joints, vestibular information from the inner ear, and memory. Different regions of the brain contribute different aspects of spatial representation. The hippocampus and entorhinal cortex, for instance, contain specialized neurons called place cells and grid cells that create an internal map of the environment and track the animal's position within it. This internal map is remarkably accurate under normal conditions. It has to be. An animal whose spatial representation consistently failed it would quickly come to grief. But it is also flexible, interpretive, and subject to illusions and distortions in ways that reveal its constructed nature. The brain fills in gaps, resolves ambiguities, and makes predictions about spatial structure based on prior experience. What feels like a direct perception of the world as it is actually a model of the world, built from incomplete information and updated continuously as new data arrives. This does not mean that the external world has no spatial structure. It means that our access to that structure is always mediated, always filtered through the particular sensory and cognitive apparatus that evolution has provided. We perceive space in 3 dimensions, not necessarily because the universe has exactly 3 large spatial dimensions, but because our perceptual systems are built to extract 3-dimensional structure from the information available to them. It is worth sitting with this for a moment. The experience of space, the immediate, undeniable, apparently self-evident fact of being here rather than there, is a product of a particular kind of nervous system, shaped by hundreds of millions of years of evolution on a particular kind of planet, at a particular scale of the universe. Creatures with different sensory systems might carve up the world differently. Creatures operating at quantum scales, if such things existed, would encounter a world in which the concept of a definite location did not apply. The experience of space is deeply tied to the scale and the biology of the experiencer. This does not dissolve the mystery of why space feels so real. If anything, it deepens it, because now we have two separate questions, where before we had one. The first question is whether space is fundamental in the physics, whether it is part of the deepest description of reality. The evidence from theoretical physics suggests the answer is probably no. The second question is why the emergent space that arises at our scale has the particular character it does, why it feels continuous, why it feels three-dimensional, why it feels like the unavoidable container of all experience. The answer to the second question likely involves both the physics of how space emerges and the biology of how nervous systems process the world. The space we experience is not just any emergent phenomenon. It is an emergent phenomenon filtered through a particular kind of perceiver, at a particular scale, under particular physical conditions. The match between the emergent geometry of the universe at our scale and the spatial categories that our brains use to organize experience is not a coincidence. It is the result of billions of years of evolution in exactly that emergent geometry. We are, in a very real sense, creatures of the emergence. Our bodies, our brains, our perceptions, and our intuitions are all products of the universe at the scale where space appears and behaves as we expect. It would be extraordinary if we did not find space convincing. We were built by it and for it, long before we had any reason to question it. Chapter 8. The Universe as Information. There is a thread running through everything we have covered so far, and it is time to pull it into the light. Whether we are talking about the holographic principle, the entanglement structure of space-time, the granular nature of space at the Planck scale, or the quantum degrees of freedom on the boundary of a region, all of these ideas share a common suggestion. The universe, at its most fundamental level, may be better described in terms of information than in terms of space, matter, or energy. This is a claim that deserves careful handling, because the word information carries different meanings in different contexts, and it is easy to slide between them in ways that obscure rather than illuminate. In everyday usage, information means something like knowledge, or news, or the content of a message. In physics and mathematics, information has a more precise meaning, rooted in the work of the mathematician Claude Shannon in the middle of the 20th century. Shannon defined information in terms of the reduction of uncertainty. When you learn the outcome of an uncertain event, the result of a coin toss, the position of a particle, the state of a quantum system, you gain information in proportion to how uncertain the outcome was beforehand. Shannon's definition is abstract and mathematical, deliberately stripped of any reference to meaning or context. It does not matter what the information is about. It matters only how many possible states the system could have been in, and therefore how much uncertainty is resolved by knowing its actual state. This abstraction turns out to be enormously powerful, and it is this precise mathematical notion of information that physicists have in mind when they talk about the universe as fundamentally informational. The first serious suggestion that physical reality might be informational in this precise sense came, as we have seen, from the study of black holes. Bekenstein's discovery that the entropy of a black hole is proportional to the area of its event horizon was a shock to the physics community. Entropy, in thermodynamics, is a measure of the number of microscopic states consistent with a given macroscopic description, a measure of hidden information. The fact that this quantity scaled with area rather than volume implied that the information content of a three-dimensional region of space was not proportional to its volume, as every intuition suggested it should be, but to the area of its surface. This was the first concrete quantitative hint that the universe stores information differently from the way our spatial intuitions suggest it should. A library stores more books as its volume increases, but a black hole stores more entropy as its surface area increases. The depth of the interior, the volume enclosed, seems to be redundant, a derived quantity that can be reconstructed from the surface, not an independent container of additional information. Hawking's subsequent demonstration that black holes emit thermal radiation, that they slowly evaporate, returning energy to the surrounding universe, deepened the puzzle. If the black hole eventually disappears entirely, what happens to the information that fell into it? If that information is destroyed, quantum mechanics is violated in a fundamental way. If it is preserved, it must somehow be encoded in the radiation emitted during the evaporation. But how information about the interior state of a black hole could be imprinted on radiation coming from near the surface was deeply unclear. The resolution of this puzzle, still being worked out in detail, points strongly toward the conclusion that the interior of a black hole is not an independent region of reality. Its apparent depth, its apparent volume, the apparently vast space inside it, all of this is a projection of the surface physics. The inside is not more real than the outside. It is a different description of the same information. And if that is true for black holes, the holographic principle suggests it may be true for any region of spacetime. The physicist Raphael Bousso formalized this into a general principle. The maximum amount of information that can be contained in any region of space is proportional to the area of the boundary of that region, measured in units of the Planck area. This is not a limitation imposed by technology or by our current understanding. It appears to be a fundamental feature of how reality stores information, and it means that space, as a container of information, is far less capacious than its apparent volume suggests. The surface is doing all the work. This points toward a picture in which the fundamental variables of nature are not fields defined at every point in a three-dimensional space, but something more like bits or qubits defined on a two-dimensional surface, interacting and evolving according to rules that produce the appearance of a three-dimensional world when viewed from the right perspective. The three-dimensional world is the story the information tells about itself. The two-dimensional surface is where the story is actually written. The physicist Eric Verlinde has extended this informational perspective in a striking direction, proposing that gravity itself is not a fundamental force, but an emergent phenomenon, a consequence of the tendency of information to organize itself in ways that increase entropy. In Verlinde's picture, the attractive pull of gravity between two masses is not caused by the exchange of graviton particles or the curvature of a space-time fabric. It is caused by the informational pressure that arises when matter is present in a region of space, changing the distribution of information on the holographic surface and generating what we experience as a gravitational force. This idea remains controversial, and it has not yet achieved the mathematical precision needed to fully replace general relativity as a description of gravity. But it points in a direction that many physicists find compelling, toward a universe in which the forces and structures we experience, including the geometry of space itself, are all downstream of something more primitive, the organization and flow of information. What would it mean to take this seriously? It would mean that the most fundamental question you could ask about any physical situation is not where things are, or how fast they are moving, or what forces are acting on them, but what information is available, how it is distributed, and how it is changing. Position, velocity, force. These would all be emergent descriptions, useful approximations valid at certain scales, but not the language in which the universe's deepest story is told. The deepest story would be told in the language of quantum information, in the entanglement structure of a vast network of qubits, in the correlations between parts of a system that has no spatial location at its most fundamental level, in the flow of information through a structure that looks like space from the outside, but is made of something entirely different on the inside. This is a genuinely strange picture. It asks us to set aside not just Newton's absolute space, not just Einstein's curved spacetime, but the very idea that geometry is the right language for describing fundamental reality. It asks us to imagine that beneath the universe we can see and measure, there is a layer of pure relationality, pure information, from which the geometry we know crystallizes into existence under conditions we are only beginning to understand. And it asks us to hold open the possibility that what we call reality, the solid, spatial, extended world of objects and distances and dimensions, is the universe's way of telling a particular kind of story about itself, a story that is true at our scale, a story we are part of and shaped by and unable to step outside of, but a story nonetheless. Chapter 9. Living at the edge of the real. There is a particular kind of vertigo that comes from thinking carefully about these ideas. Not the sharp, alarming vertigo of standing at the edge of a cliff, but something slower and quieter. The feeling of the ground becoming uncertain beneath your feet. Not suddenly, but gradually, the way certainty sometimes fades when you examine something you have always taken for granted. Most of us move through life without questioning the reality of space. We wake in a room with walls at a certain distance. We walk down streets of measurable length. We look up at a sky that extends outward in all directions, and the extension feels as solid and certain as anything we know. Space is the medium of all experience, and questioning it feels a little like questioning the validity of questioning itself. A loop that seems to lead nowhere useful. And yet, the physics we have explored in the preceding chapters does not ask us to doubt our experience. It does not suggest that the walls of the room are not where they appear to be, or that the distance to the nearest star is somehow mistaken. The emergent space we inhabit is real at the scale we inhabit it. The measurements are genuine. The geometry holds. What the physics asks us to consider is something more subtle, that the reality we experience, accurate and reliable as it is at our scale, may not be the deepest reality available, that beneath the geometry there is something else, and that something else does not look like space at all. This is not, historically speaking, an entirely new situation for humanity to find itself in. Science has repeatedly revealed that the world as it appears to us is not the world as it fundamentally is, and that the gap between appearance and underlying reality is often deeper and stranger than anyone anticipated. The ground beneath our feet feels solid and still. It is neither. It is a thin, rocky crust floating on a slowly churning mantle of partially molten rock, carried on a tectonic plate that moves several centimeters each year, on a planet rotating at more than 1,000 kilometers per hour at the equator, orbiting the Sun at roughly 30 kilometers per second. None of this motion is felt. None of it disturbs the apparent stillness of a quiet afternoon. The appearance is coherent and stable. The underlying reality is dynamic and vast. The table in front of you feels solid. It is almost entirely empty space. The atoms that make up its surface are themselves mostly void. A tiny nucleus surrounded by a cloud of electrons so diffuse that the ratio of matter to emptiness within a single atom is roughly comparable to the ratio of the Sun to the entire solar system. The solidity you feel when you press your hand against the table is not caused by matter touching matter. It is caused by the electromagnetic repulsion between electron clouds, a quantum mechanical effect that has nothing to do with solidity in the everyday sense of the word. The table is real, its solidity is real, but the underlying nature of that solidity is nothing like what it appears to be. In both of these cases, and in many others like them, the discovery that the underlying reality is different from the apparent reality did not make the apparent reality less useful, less meaningful, or less true at the scale where we encounter it. The ground is still steady enough to build on. The table is still solid enough to rest things on. The emergent properties are reliable and consistent, even when the fundamental picture is strange. The same logic applies to space. If space is emergent, if it arises from a deeper layer of quantum information and entanglement, this does not make the distances we measure unreliable or the geometry we use to navigate the world invalid. It means that those measurements and that geometry are real features of an emergent structure, accurate at the scale where we apply them, even if they dissolve into something unrecognizable at a scale far below anything we can directly probe. But there is something that changes, and it is worth naming clearly. What changes is our sense of what questions are the fundamental ones. If space is not fundamental, then the questions that seemed most basic, where is this? How far is that? What is the geometry of the universe? Turn out to be questions about an emergent structure rather than about the bedrock of reality. They are important questions, and their answers matter enormously for understanding the universe at the scales we can observe. But they are not the deepest questions available. The deeper questions are about the structure from which space emerges, about the nature of the quantum degrees of freedom on the holographic boundary, about the rules governing the entanglement patterns that give rise to spatial geometry, about why certain configurations of quantum information produce the particular kind of emergent space we find ourselves in. With three large spatial dimensions, with the specific curvature properties described by general relativity, with the particular value of the cosmological constant that allows galaxies and stars and planets and living things to exist. These are questions that current physics cannot yet fully answer. They sit at the frontier, not the comfortable frontier where the next experiment is already designed and the next result is eagerly awaited, but the uncomfortable frontier where the right questions are still being formulated and the mathematical tools needed to answer them are still being invented. And this is, perhaps, the most honest place to sit with all of this. Not at the point of a grand conclusion, not at the threshold of a final answer, but somewhere in the middle of a very long and very serious investigation into the nature of something so fundamental that the investigation itself keeps changing what fundamental means. The physicists working on these problems are not mystics or speculators. They are careful, technically sophisticated researchers who have spent careers mastering the most demanding mathematics available and who are using those tools to follow the implications of well-tested theories to their logical conclusions. The conclusions are strange, but strangeness has never been a reliable indicator of falsehood in physics. The history of the field is largely a history of the strange turning out to be true. What does it feel like to live at the edge of this understanding? To go about an ordinary day in an apparently solid spatial world, while knowing, at least intellectually, that the solidity and the spatiality may be emergent properties of something that has no solidity and no spatiality at all. For most people, most of the time, it feels like nothing in particular. The knowledge is too abstract, too far removed from the scale of daily experience to change the texture of life in any immediate way. But occasionally, in a quiet moment, looking up at a clear night sky, watching the light of stars that left their sources before humans existed, something of the strangeness does filter through. The sky above is not just vast. It is, if these ideas are correct, a surface of an emergence, a large-scale pattern produced by something far beneath the reach of any telescope, something that does not have a sky or a distance or a darkness of its own. The stars are real, the light is real, the wonder is real, but the space they occupy may be, in the deepest sense available to us, a kind of crystallization, reality taking on a shape at our scale and for our kind of perceiver that it does not fundamentally possess. That thought, held gently and without urgency, is one of the quieter and more remarkable things that careful science has given us to rest with. Chapter 10. What remains when space dissolves? We have travelled a long way from the opening question. We began with something that seemed almost too simple to ask. Whether space, the vast and silent container of everything we have ever known, is real, and we have moved, slowly and without hurry, through 2,000 years of thinking about the nature of that container, from the ancient Greeks and their ether-filled heavens, through Newton's absolute and infinite grid, through Einstein's dynamic and curving fabric, into the strange territory of quantum mechanics and entanglement, and finally to the frontier where physicists are seriously proposing that space is not the foundation of reality, but something that rises from a foundation we have barely begun to see. It is worth pausing here near the end to take stock of what we actually know and what remains genuinely open. What we know is this: the two greatest theories of the 20th century, general relativity and quantum mechanics, each transformed our understanding of space in ways that moved it further from the simple, self-evident container of everyday experience. General relativity showed that space is dynamic, that it curves and bends and ripples in response to matter and energy, that it is not a passive background, but an active participant in the physics of the universe. Quantum mechanics revealed that at the smallest scales, the concept of a definite location loses meaning, that particles do not occupy positions in space until they are measured, and that entangled particles share correlations that the distances between them cannot explain. Every serious attempt to combine these two theories, to write a quantum theory of gravity, has encountered the same stubborn suggestion that spacetime, as a fundamental structure, is not where the story begins. The holographic principle, emerging from string theory, indicates that the physics of a volume of space can be completely described by a theory on its boundary, in one fewer dimension, raising the possibility that at least one dimension of space is emergent. The mathematics of entanglement and geometry suggests that the connectivity of space, the very fact that regions are joined together in a continuous fabric, is a reflection of quantum entanglement in an underlying non-spatial description. Loop quantum gravity proposes that space is granular at the Planck scale, that the smooth geometry we experience is an approximation that breaks down at distances too small for any current experiment to probe. None of these approaches is complete. None has been fully confirmed by experiment. The theory of quantum gravity that would make all of this precise and testable remains one of the great unfinished projects of modern science. What we have are strong theoretical indications, mathematical structures of remarkable consistency and depth, and a growing consensus among the physicists who work most closely with these questions that space is not the bedrock they once assumed it to be. What remains open is perhaps more interesting than what is settled. We do not know what the fundamental substrate of reality actually is. We have candidate descriptions, quantum degrees of freedom on a holographic boundary, networks of entangled qubits, pure relational information, something not yet named. But we do not have a complete and tested theory that specifies precisely what is there when the geometry dissolves. We do not know why the emergence produces the particular space we find ourselves in. 3 large dimensions, the specific constants of nature, the conditions that allowed complexity and life to develop. We do not know whether the emergence is universal, whether every possible configuration of the underlying substrate produces something like space, or whether our spacetime is one of many possible emergent geometries arising from the same fundamental layer. These are not questions at the edge of a completed science. They are questions at the center of a science still very much in progress. And that is, in its own way, a remarkable thing to sit with. We live in a moment when the most basic question you could ask about the physical world, what is the space we inhabit, and is it real, is genuinely unanswered. Not because the question is unanswerable in principle, but because the science that would answer it is still being built. There is something quietly wonderful about that. The universe has been here for nearly 14 billion years. Humans have been asking systematic questions about its nature for only a few thousand. The fraction of cosmic time that has been spent on the investigation is vanishingly small, and in that brief interval, the investigation has already reached the point where the container of all things is itself in question, where the stage has become the subject, where the arena in which all of physics was assumed to happen is now the thing that physics is trying to explain. This is not a crisis, it is a depth. Every time science has moved to a deeper layer of explanation, from the motion of objects to the atoms they are made of, from atoms to the quantum fields within them, from fields to the information structures that may underlie everything, the world has not become less real. It has become more interesting. The richness of what is has always turned out to be greater than any previous picture of it could accommodate. If space is emergent, then reality is not smaller than we thought. It is larger. It contains space, produces it, sustains it, fills it with light and matter and the slow turning of galaxies. And it contains whatever space emerges from, and perhaps layers beyond that which we have not yet imagined. The dissolution of space as a fundamental category does not leave us with nothing. It leaves us with the question of what is actually there, which is a far more interesting thing to be left with than a final answer. There is a particular kind of peace that comes from sitting at the edge of a genuinely open question, not the restless peace of a problem solved and filed away, but the quieter peace of a mystery that is real, that is being taken seriously, and that the best minds of our time are working on with patience and rigor and appropriate humility. The question of whether space is real is that kind of mystery. It will not be answered tonight. It may not be answered in our lifetimes, but it is being asked carefully, and the asking itself is one of the finer things that minds like ours have ever done. The stars above are, for now, exactly where they appear to be. The distances between them are, for now, exactly as vast as they seem. Whatever lies beneath the geometry, whatever the deeper layer of reality turns out to be, it has arranged itself at our scale and for our kind of perceiver into something of extraordinary beauty, into light crossing unimaginable distances, into a darkness that holds more structure than the eye can see, into a universe that is at every scale we have yet managed to examine, stranger and richer and quieter than anything we could have expected. That is perhaps enough to rest with tonight. If this was a good companion tonight, a like or a subscribe helps other curious minds find their way here.